Imagine a world with unlimited energy, a world where power shortages and energy crises are things of the past. Could black holes be the answer? Today our planet faces a significant energy conundrum. Traditional sources like fossil fuels are rapidly depleting and causing environmental harm, while renewable sources like solar and wind, though promising, can't keep up with our growing energy demands. Amidst these challenges, scientists are exploring revolutionary concepts, and one such idea is harnessing energy from the most powerful entities in the universe, black holes. These cosmic phenomena are not just intriguing because of their mysterious nature, but also for their immense energy potential. If harnessed, the energy from black holes could change the way we power our world, unlocking possibilities beyond our wildest dreams. So let's dive into the mysterious and fascinating world of black holes. Black holes are not just space oddities, they are powerful forces of nature. To truly grasp the potential of black holes as energy sources, we first need to understand what they are and how they come to be. Imagine a star, far more massive than our sun, reaching the end of its life. It collapses under its own gravity and in the process creates an area in space where gravity is so strong that nothing, not even light, can escape from it. This is a black hole. At the heart of a black hole, we find a point of infinite density known as the singularity. It's a place where our understanding of physics breaks down and the rules of the known universe no longer apply. Surrounding this is the event horizon, the point of no return. Once anything crosses this threshold, it's destined to be crushed into the singularity. The gravitational pull of a black hole is so immense that it warps the space around it, causing nearby objects to move along curved paths. It's like a cosmic whirlpool pulling everything towards it. This incredible pull also causes the creation of an accretion disk, a spinning disk of gas, dust, and other materials that circles the black hole. It's here in this chaotic and violent maelstrom that the potential for energy extraction lies. But black holes aren't just powerful, they're also incredibly efficient. A black hole can convert up to 10% of the mass of an object into energy as it devours it. Compare that to nuclear fusion, the process that powers our sun, which only converts about 0.7% of mass into energy. The difference is staggering. So we have these cosmic monsters, these black holes, that are not only incredibly powerful but also extremely efficient. And while they might seem like destructive forces, they could hold the key to our future. These cosmic monsters, with their immense power, could potentially be our future power stations. The challenge now is figuring out how we can harness this power safely and effectively. The idea of harnessing energy from black holes is not new. Over the years, scientists and researchers have proposed various theories and concepts centered around this fascinating idea. The two main methods that have been suggested are Hawking radiation and accretion disks. Firstly, let's talk about Hawking radiation. Named after the renowned physicist Stephen Hawking, this theory suggests that black holes are not completely black but emit small amounts of thermal radiation due to quantum effects near the event horizon. These particles, known as Hawking radiation, could theoretically be captured and converted into usable energy. While the concept is intellectually stimulating, the practicality of capturing this minuscule radiation from a safe distance remains a significant challenge. Now let's move on to accretion disks. These are essentially disks of cosmic gas and dust that spiral into a black hole, heated to extremely high temperatures by the immense gravitational energy and emitting vast amounts of radiation in the process. This radiation, which is much more substantial than Hawking radiation, could potentially be harnessed for energy. The power generated by accretion disks is so great that it outshines all the stars in the same galaxy. Imagine for a second the possibilities if we could tap into even a fraction of that energy. But as with Hawking radiation, the practical challenges are immense. The technology required to capture and convert this energy is far beyond our current capabilities. And let's not forget about the logistical and safety issues involved in getting close enough to a black hole to harness this energy. In essence, the theories of energy extraction from black holes paint a picture of immense potential. The energy trapped in these cosmic phenomena is mind-bogglingly vast. However, the challenge lies not in the theory but in the implementation. Harnessing this energy will require technological advancements that are perhaps centuries away. But who knows what the future holds? After all, the universe is full of surprises. One of the most intriguing ideas for harnessing energy from black holes comes from the late physicist Stephen Hawking. Imagine this. Black holes, those insatiable cosmic vacuums, aren't just gobbling up everything in their path. Instead, they're also emitting something, a phenomenon known as Hawking radiation. Unveiled by Stephen Hawking in the mid-70s, this theory proposes that black holes aren't entirely black but emit tiny particles, hence the term radiation. Here's a simplified version of how it works. At the edge of a black hole, the event horizon, pairs of particles and antiparticles spontaneously pop into existence, a quirk of quantum mechanics. Usually they annihilate each other almost instantly. But if one particle falls into the black hole while the other escapes, the black hole loses a tiny bit of mass equivalent to the energy of the escape particle. This escaping particle is what we call Hawking radiation. So what does this mean for energy extraction? Well, in theory, if we could collect these particles, we might convert their energy into a form we can use. It's a tantalizing prospect, considering the sheer number of black holes in the universe, each potentially a source of near-limitless power. But of course, it's not that simple. The first challenge is the fact that Hawking radiation is incredibly weak. Detecting it, let alone harnessing it, with our current technology is beyond our reach. And then there's the matter of distance. Even the nearest black hole is thousands of light years away, making any current proposal for energy extraction a far-off dream. Nonetheless, the idea of harnessing black hole energy through Hawking radiation is a testament to human curiosity and ingenuity. It pushes the boundaries of what we think is possible and drives us to continue exploring the universe's mysteries. Hawking radiation, if harnessed, could provide us with an almost infinite energy source. Another potential source of energy from black holes is the accretion disk. Now, you might be wondering, what is an accretion disk? It's a flat, disk-like structure of matter that spirals into a black hole. Think of it like water spiraling down a drain, but instead of water, it's gas, dust, stars, and even light, and instead of a drain, it's a black hole. As this matter spirals into the black hole, it speeds up and heats up, reaching temperatures so high that it shines brightly, releasing an incredible amount of energy. This is where the potential for energy extraction comes in. The energy produced by an accretion disk is not just substantial, it's astronomical. We're talking about a powerhouse of energy that makes our sun look like a mere candle in comparison. But how can we harness this energy? Well, one potential method is to place a Dyson sphere or a similar structure around the accretion disk to capture the energy it emits. This is, of course, a highly theoretical notion and not something we can currently achieve with our existing technology, but it does provide a fascinating glimpse into the potential future of energy production. Now, it's worth noting that the energy from an accretion disk comes with its own set of challenges. For one, the environment near a black hole is incredibly hostile, and any structure we build would need to withstand intense radiation and gravitational forces. Moreover, capturing the energy efficiently would be a significant challenge as the energy radiates in all directions. Despite these challenges, the potential rewards are too great to ignore. If we could harness even a fraction of the energy produced by an accretion disk, it could revolutionize our understanding of energy and provide a nearly limitless power source. Imagine a future where black holes are not just fascinating celestial objects, but vital components of our energy infrastructure. The energy produced by accretion disks is astronomical, to say the least. Harnessing energy from black holes is a technological challenge of epic proportions. The sheer magnitude of the task is something that at present is beyond our current technological capabilities. However, this doesn't mean it's impossible. It merely means we have a long, exciting journey of scientific and technological innovation ahead of us. Let's picture it for a moment. To extract energy from a black hole, we'd need to reach it first. Currently, our fastest spacecraft would take thousands of years to reach the nearest black hole. This calls for advancements in space travel technology, perhaps involving concepts like wormholes or warp drives, which are currently purely theoretical. Once we reach a black hole, we'd need to survive its extreme environment. The gravitational forces near a black hole are immense, capable of spaghettifying anything that gets too close. We would need to develop technology capable of resisting these forces or operating at a safe distance. Then let's consider the energy extraction process. The techniques we've discussed, such as harnessing Hawking radiation or tapping into the energy of accretion disks, are complex and still largely theoretical. They would require technological breakthroughs in fields like quantum physics, materials science, and energy storage and transmission. But what if we could overcome these challenges? Imagine a future where black holes serve as cosmic power plants, providing virtually limitless energy. This could revolutionize our civilization, powering advanced technologies and making interstellar travel a reality. It could solve our energy crisis and help us become a truly spacefaring species. Of course, this is all speculative. We're still in the early days of understanding black holes, let alone harnessing their power. But it's a tantalizing prospect, one that drives scientists and researchers across the globe to continue exploring the universe and pushing the boundaries of what's possible. The path is challenging, but the rewards could be astronomical. Harnessing energy from black holes is not just a scientific and technological challenge, but also an ethical and safety one. Even as we marvel at the potential of black holes as an energy source, we must consider the ethical implications. The cosmos is a shared resource, and manipulating a force as powerful as a black hole could have far-reaching consequences. Is it morally right for us to interfere with these celestial bodies? And if we do, what safeguards should be in place to ensure we don't inadvertently cause harm? Then there are the potential risks. Black holes are, by their very nature, unpredictable. Their immense gravitational pull could be a threat if we don't fully understand how to control the energy extraction process. What if an accident caused a black hole to shift or change in a way that threatened nearby celestial bodies or even Earth itself? There's also the question of who gets to harness this energy. In a world where resource inequality is already a major issue, could black hole energy become another tool for the powerful to dominate the less fortunate? How do we ensure fair and equitable distribution of this potentially limitless power source? And let's not forget the potential impact on our own planet. If we become reliant on black hole energy, what happens to our efforts to conserve Earth's resources and reduce our environmental impact? Would we become complacent, knowing we have a seemingly endless supply of energy in the cosmos? While these questions may seem daunting, they are not insurmountable. Rigorous ethical debates, stringent safety measures, and robust regulatory frameworks could guide us. International cooperation will be key, ensuring all nations have a say in how we explore and potentially exploit these cosmic powerhouses. The conversation around black hole energy extraction is as much about our values, our aspirations, and our fears as it is about the science. It's a dialogue we must have, openly and honestly, as we stand on the cusp of a new era in energy production. The promise of unlimited energy comes with its own set of dilemmas. The idea of harnessing energy from black holes is as fascinating as it is daunting. This concept, once only the stuff of science fiction, is now a topic of serious scientific inquiry. It's a testament to the human spirit of exploration and innovation. We've delved into the mysteries of black holes and the potential they hold for solving our energy conundrum. We've explored the concepts of energy extraction from these cosmic entities, from the theoretical Hawking radiation to the intense energy of accretion disks. We've considered the immense technological advancements that would be required to tap into this power, to capture and convert it into a form we can use. This is no small feat. It's a task that would push the boundaries of our current understanding and capabilities. We've also addressed the potential energy output and efficiency of harnessing black holes. The energy we could potentially extract from these cosmic phenomena is mind-boggling, dwarfing all our current energy sources. But it's not just about the potential benefits. We've also highlighted the ethical and safety considerations, the need to balance our pursuit of energy with our responsibility to the universe we inhabit. We've contemplated the possible applications of black hole energy, from revolutionizing space exploration to powering our industries. We've discussed the potential astrophysical impacts, the changes it could bring to the dynamics of galaxies and the space surrounding black holes. The idea of manipulating black holes for energy is not without its critics and skeptics. We've addressed the public perception and acceptance, the environmental considerations, and the need for global collaboration and regulation. This isn't just about science and technology, it's also about our society, our values, and our future. In the grand scheme of alternative energy sources, black hole energy extraction could play a complementary role. It could become part of a diverse energy portfolio, alongside renewable and non-renewable sources. The question remains, are we ready to tap into the power of black holes?